It only works if you have this going on here. All right. Chapter 2. We finally get into some formulas, folks. We finally get into what I call the essence of physics. Okay? So, what you need to have out as we go through these chapters, pretty much here on out, is your or a sheet that is dedicated to formulas. Okay? It needs to be a separate piece of paper. I don't want it on anything else because, again, you get to use these on quizzes and tests. Okay? All right. So as I mentioned yesterday, this chapter is very busy. Okay? It's going to really ramp up next week. So make sure that you stay on top of it. Okay? And really what next week is all about is we're going to take pretty much almost a single concept, but work at it multiple ways. All right. So this first section is dealing with displacement and velocity. And these are terms that you should hopefully have heard from our note taking. And after this section, these are the objectives that we should be able to do. This is what we're going to be doing throughout today. We're going to describe motion in terms of frame of reference, displacement, time, and velocity. We'll calculate the displacement of an object traveling at a known velocity for a specific time interval. And then lastly, we'll construct and interpret graphs of position versus time. But right off the bat, we see a term called displacement. What does displacement mean? Okay, A to B distance. Okay. In a way, it does have to do with distance, but you have two different words. You have displacement and distance, right? So usually when you have two different words, you might have two different meanings, and that is the case here, okay? So we're going to distinguish displacement from distance and how we use those differences in what we calculate, okay? All right. We are looking at one-dimensional motion, okay? That's your favorite band, isn't it? One Dimension?
What?
Exactly. Wait, it's One Direction.
Yeah.
I knew that.
It says it right there.
I know. I was making a joke. Oh. Anyway, so to simplify the concept of motion, we're going to make it very basic, okay? We're only going to be looking at motion that is going in one direction, or what we call one dimension, okay? Eventually, when we start getting into multi-dimensional, we're going to be having motion going in, obviously, multi-directions. But if we think about what this means, if we look at a train that is on a track, okay? The train that is on a track can only go forwards or backwards, okay? It can't go side to side, can't really turn because we're thinking about going straight right now, okay? So in order to measure motion, we often have to use a frame of reference, okay? What's a frame of reference? Who can give me an example of frame of reference? Oh, there's so many hands up. It's really hard to pick one. What? Latitude and longitude. Okay. When you say latitude and longitude, what do you mean by that when you talk about frame of reference? Okay. So you're talking about the coordinate systems and directions. Okay. What were you going to say?
Like trees going past the skiers. Is the skiers going downhill? Trees can be frame of reference to stationary trees.
Yes. Okay. So I knew what you were getting with there. back there. But yes, when we talk about a frame of reference, we have to take objects that are in motion and compare it to objects that are stationary. Okay? So, as I walk in front of my desk, okay, your frame of reference is that setting right there. You are witnessing my motion against the stationary desks. Okay? Like Gage said, what do you say, skier? The skiers and the trees, okay? Those trees are stationary, and we can observe the motion of that skier in regards to the frame of reference of the trees, okay? So, it's a system of specifying the precise location of objects in space and time. You saw me in front of that desk, okay? That is your frame of reference. When we talk about frame of reference and velocity and everything, we are talking about displacement, that term that we just mentioned, okay? Displacement is a change in position, but it is not always equal to the distance that is traveled. We measure, well, both distance and displacement in meters. But let's talk about this displacement idea. Okay? I'm gonna start on, well, I'll start here. I'm gonna go this way. Okay, starting on this colored tile. Each tile is about 12 inches. So we'll use tiles as our reference. So 1, 2, 3, 4, 5. How many tiles did I just travel? 5. Okay? I'm going to return trip. 1, 2, 3, 4, 5. Round trip, how long was my trip? 10 tiles. Okay? That was my distance. Distance measures total distance traveled. Okay? Now, let's change it and go to displacement. 1, 2, 3, 4, 5. Okay, so far I've traveled 5 tiles. My return trip. 1, 2, 3. So I stop here. 3 tiles on the way back. What is my actual displacement that I would use? 2 tiles. Exactly. Displacement is the distance between where you started and where you stopped. Okay? It's not your total round trip. So let's think about other examples here. We have a space shuttle takes off from Florida. If you've never seen I know we don't launch shuttles right now, but if you've never seen a rocket launch, it is phenomenal. Anyway, space shuttle takes off from Florida, circles Earth many times, finally landing in California. While the shuttle is in flight, the photographer flies from Florida to California to snap some shots of them walking off the shuttle. Who undergoes the greater displacement? The astronauts or the photographer? And mind you, astronauts went all the way around the Earth many times, landed in California. Who would have the greater displacement? Neither. Why do you say neither?
Because they started in Florida and ended in California.
Exactly. The displacement is totally the same. Because they started in the same location. We're making the assumption they started in the same location. And they ended at the same location. So their distance from where they started and stopped is the same, even though the shuttle went many times around the Earth. Now, think about this. What would be the difference between displacement of a photographer flying from Florida to California and the astronauts flying from California, Florida? What do you think? What do you think? Aha. One of them would be considered negative. Where did that go? I guess I didn't put it on there. Yeah. One of them would be negative. Okay? And then you ask yourself, well, which one would be negative? And it's really all dependent on the system that you set up. Okay? When we're talking about displacement and velocities, what we're really beginning to talk about are vector motions. Okay? And that means that we have to pay careful attention to direction. Now, direction is going to ultimately determine what our sign will be, because our signs, whether it be negative or positive, are going to inform the reader about which direction the object is traveling. Okay? A very rudimentary one is to simply do this: north, east, south, west. Okay? And anytime you are traveling north or east, it is positive. Anytime you travel south or west, that is negative. Okay? By assigning signs like positive and negative, that incorporates itself into the mathematical solutions, which then ultimately tell us what direction the object was going. So again, this object is moving from right to left, that is negative. This object is moving left to right, that is positive. And so it tells us that those on the right are moving to the left or west. Okay? So here's our first formula for the year. Okay? Make sure you write this down. First formula for the year, and that is average velocity. Average velocity is the total displacement divided by the time interval during which the displacement occurred. So you have average velocity is equal to delta x divided by delta t. Again, anytime you see the letter delta, that means change in. So xf, meaning the final position, minus xi, the initial position. Okay? Divided by time. And you may, if you want to, do it both in variable format and or word format. Okay? And just like with speed, the SI unit is meters per second. Okay? There is a key difference though. There is a key difference, and this is muy importante as I get closer to the microphone for those at home. When you're talking about velocity, or really anything vector related, which velocity is a vector property, okay? You must, when possible, include the direction in your answer, okay? Velocity, as we'll see a little bit later, is more specific than speed. Okay? Let's look at an example here. You are traveling to a friend's soccer game. Absolutely. And the soccer game is 370 kilometers west. Okay? That is a negative direction. Okay? That's why I have negative there. Along a straight Illinois highway. You left your house at 10 a.m. and arrived at the game at 3 p.m. What is your average velocity? Okay? So, again, we're solving for average velocity. We can use that formula without having to arrange it. Now, you'll also notice that we're talking about kilometers. Okay? And the SI we just saw is in meters per second. there are some situations, whether told or you just figure that, well, I mean, this is a pretty big number if you think about it in terms of meters. There are times where you can just keep it in kilometers, okay? So, when you solve this, again, you notice that, I get a question. You see that I incorporated that negative sign into my 307, my displacement, because we are traveling west, okay? And here's where that negative sign comes into play. Once you take your displacement, again, because it's only talking about a one-way trip. So that's why we're able to use the total distance, basically. Divided by the time, and again, I'm keeping it in terms of kilometers per hour because that's what makes sense in this situation, okay? You notice that when I do the calculation, I get a negative 74 kilometers per hour. What that means for your answer is that negative indicates the direction. So, to finalize your answer, you need to remove that negative sign and replace it with the direction the vehicle or object was going. Does that make sense? Okay? Again, don't leave the negative sign in your answer. Replace it with the direction. So next, we have, circle that. We have Andra, okay? During a race on level ground, Andra runs with an average velocity of 6.02 meters per second to the east. What is Andra's displacement after 137 seconds? Now, I can't bring up my little tools here. Darn it, I was gonna have fun with that. So anyway, I'm gonna get out of here. Okay, go here, and I'm going to try and do this. Okay, I'm gonna brighten this up just a hair. Okay, so write down. This is what I do. You're gonna notice I do the baby step method a lot. So average velocity is equal to delta x over delta t, right? But what do we know? Okay, so coming over to the side, I'm just going to list my variables. First of all, what are we solving for in that question? Displacement. So that's our delta x. Okay, and so what do we know? What is our average velocity that has been given? East. Now, it gives us the direction that Andrea is traveling. So would this be a positive or a negative value? Be positive. Again, directions north and east are considered positive. Okay? So we don't have to put any negative sign in there. What about time? 137 seconds. All right. So we're solving for x. That means we need to isolate it. How do I isolate x in this equation? I'm going to multiply both sides by delta t. I'm going to get the formula of delta x is equal to average velocity multiplied by change in time. So I take my 602 meters per second, multiply it by our 137 seconds, which allows for seconds to cancel out. And what do I end up getting for an answer? Again, going back to sig figs, we go by the lowest number of sig figs. Okay, so how many sig figs should our answer be in? 3. Okay, 602 has 3, 137 has 3, so that makes it easy. So what do I get?
I got 82,500.
So you got 82,500, right?
Yeah.
Okay. Okay, so
It would just be 825.
so 825, and that's in meters. So I double check that.
I just did it in my head.
Oh, okay.
Yeah.
So it's all right. She travels 825 meters to the east. Okay, and that's how you work this particular equation. Questions on this equation or this formula? No, we got a few more slides to go. All right. Hello. All right. So again, just quickly distinguish between velocity and speed. Velocity is much more specific in its description. It gives a magnitude along with a direction. So that's why it's very important that when you are solving for velocity, that you do remove that negative sign and include the direction. Okay? But you essentially solve speed the same way that you would velocity. So here's your second formula if you need it, okay, for speed. Distance traveled by time of travel. So speed takes in your total distance that you have traveled. Now going back to that space shuttle and photographer example, the first one where the space shuttle launched, went around the Earth many times and returned to California, its distance would be significantly larger than that of the photographer. Okay. Just real quick, when we start talking about velocity and speed, and start looking at position versus time graphs, we can look at the slopes of the lines of an object's motion to make predictions about the velocity itself. If we look at object 1, it's the one that is going at an angle here. It has a positive slope, therefore it has a positive velocity. Object 2 is completely flat, horizontal, zero slope, meaning the velocity is not changing. And then object 3, negative slope, we have negative velocity. Okay. Notice where position and time are on the graphs as well. Position is the y-axis, time is on the x-axis. And one last thing we really don't do a whole lot of, and that is instantaneous velocity and the determination thereof. What this is that we can determine the slope of a line that is tangent to an object that has maybe not such so consistent velocity. Okay, notice how we've got a curve in our line. Okay, so it might be a little difficult to pinpoint with our typical measures. Instead, we can take a line that is tangent to any point on that line, on that graph, and measure the slope. That slope would then give us the velocity of that object at that exact moment in time. There's instantaneous speed that we'll talk about sometime later in the future. And that's a very similar concept, except we can measure using a specific tool in every one of your cars. You know what it is? It has the name built right into it. What's that? Speedometer. So yeah. So your speedometer is telling you the exact speed at that exact instant of time. Okay? Questions on this? Now your homework this evening is going to be roughly the same length. There is a question on there that I noted that it is a thinker. Okay? It is a thinker. So try your best. Think about the scenario itself. Okay? So I'm going to go ahead and pause or stop the recording.